Now under VSEPR, let's see what's going to happen when we start mixing our orbitals. So if we have Sp3 hybrid, that means we're taking our s and all three p orbitals, we're mixing them all together. So we have 1 and 3 give me 4 orbitals, 4 valence orbitals that are mixing. So we're using all the s and the p orbitals on the valence level. We're going to get a total of 4 electron regions from those valence orbitals. Notice the symmetry between this theory and VSEPR. We have 4 orbitals here. They make 4 bonding regions here. So if you add up the x's and e's in AXE notation, that should equal the same number as Sp3. So AX4, Sp3 will be the same geometries. And so here's our methane molecule, CH4. You can see that what we've got is the hydrogen with its 1s orbital with 1 electron in it. It comes close enough to carbon. Now carbon started out looking like this. The carbon had 2 electrons in the s orbital, 1 and 2 in the p, and a totally empty p orbital. That's when it was originally by itself. Once it gets close to those hydrogens, though, what's going to end up happening is all of these are going to mix together in the blender and taste like cherries and anchovies at the same time. In other words, the flavor, the energy of each of these orbitals is going to be averaged with the energy of the bottom orbital to give us the new energy, which we expect to be 2/3 of the way between them. And that's what we see. We get a total of 4 portions of cherry and anchovy out of the blender, 4 orbitals, all the same flavor and energy, all Sp3s. We now have a slot for each of the 4 electrons. Notice that this process is energy neutral. Yeah, these had to go up in energy, but these came down in energy, which means that overall carbon is no happier or more upset than it was originally. What advantage does that give it? Well, we know that it's going to be making new orbitals to make the bond with that hydrogen atom. When those hydrogen atoms with only 1 electron in each come nearby, they can overlap and share it so that we have an up arrow and a down arrow, up spin and down spin, both being paired up. We'd have to have a totally different quantum number scheme for this, and we're not even going to touch that. But you can see that this is all that we're talking about. We're mixing our orbitals, we're getting our energies to be the weighted average between them, and then we end up sharing an electron into those. Now, let me give 2 more examples of Sp3 hybrids. Suppose we had the ammonia molecule. Remember, we did this one as a Lewis structure a while back, and I also brought it up as an example of why we have to make sure we handle everything inflated in 3 dimensions, not in flatland. Let's see if this can explain the same sort of thing. So here's our isolated nitrogen atom. We got up to our 2s orbital, totally full. We got to our 2p orbital, totally full. Well, half full, I should say. 1 electron in each. If we were totally mixing these, I'd still end up with one of these being totally filled with electrons. I'm going to have 3 half-filled Sp3 hybrids, and they're all the same energy. All 4 of these are the same energy. Now these are spots where we can build a bond, because we need to. We need to pair up with another electron in order to fill each of these orbitals. And hydrogen is just the man for the job. Hydrogen has 1 electron. If we bring it in, these all become bonds. And I'll remind you, I'm not implying energy here. I'm just showing that they're right there binding in. I can't overlap them and show them at the same energy, but they are. And so we end up having them all be the same energy as they were originally. Didn't cost us anything to make these, as far as this goes, in the mixing. So by mixing them, we were able to make this happen. Notice that it predicted that we would have a lone pair that doesn't bond at all, and we'd have 3 bonding regions. In other words, what we just predicted was the AX3E geometry, having the same shape as Sp3. Notice what we're saying is we have one s orbital mixed in. We have 3 p orbitals, meaning we have a total of 4 orbitals. We have a total of 4 regions of space, aka orbitals, that have electrons in them. Total of 4, 3 plus 1 is 4. Total of 4, 3 plus 1 is 4. These end up giving the same result either way. How about we look at water, one of our favorite molecules of all time? So you can see that we have the 2 electrons down in the 1s orbital. We're just not showing them because they're not valence level. But we had 2 electrons down there. 4, 6, 8. There's all 8 electrons that would be around oxygen, and all 6 of our valence electrons, 2, 4, and 6. Everything's filled following all of our principles. We then throw them all in the blender and mix them. All of our orbitals are now the same energy. I have 2 lone pairs that are not going to be shared. I have 2 half-filled orbitals that need to share in order to fill. We bring in our hydrogens, and we predict that we're going to have water in Lewis structure form. We predicted it was going to have 2 bonding regions and 2 unshared pairs of electrons. There's our 2 unshared pairs of electrons right here, our 2 bonding regions right here. From this, we would predict our overall geometry to be tetrahedral for the electron groups. We'd expect a bent geometry for our bonding regions. And because of the polarity, we're going to still expect that water is going to look like this. We'll have our 2 non-bonding electrons over here, and then over here. Oxygen is more electronegative, so when we combine the electronegativity and the polar arrows from both sides, we end up with this polar arrow for the whole thing. There's water under either theory. We get the exact same result.